All right, example 5. Find the point on the line 2x plus y equals 8 that's closest to the point 2, negative 5. Okay. I kind of like to graph this just so you can see what they're asking us to do. Let's go this way. So if we take a look at 2, negative 5, first of all, 1, 2, 1, 2, 3, 4, 5. That's the point 2, negative 5. And then we have the line y equals negative 2x plus 8, right? You move the 2x over, change the sign. Plus 8, 1, 2, 3, 4, 5, 6, 7, perfect, 8. And a slope of negative 2, so you do that down to. That's pretty good. All right, so this line has infinity points on it, right? One point on this line is closest to that point, and we're trying to find that specific point. All right, and that's what it is they're asking us to do. And we're going to use this optimization technique to do this. Now, by drawing a picture of the situation, it might give me more insight as far as how to do this. I'm just going to put some generic point out here. Let's say this point right here is the point x comma y. I'm going to say that's the point that's closest. Okay, what are the coordinates of x, y right now? X, I don't know either. Yeah, we don't know. But we're trying to find that. That looks, to me, by my eyeballs view there, it looks pretty close to what it should be, right? Mm-hmm. Seems like, straight to it. But 1, 2, 3, 4, 5 in a little bit, down 2 in a little bit, right? So somewhere in that general range. I'm guessing my answer is going to be somewhere in that general range. Not perfect, but close. And we're trying to find the length of, let's see here, that looks good. We're trying to make that the smallest it can be. Let's just call that little d. All right. And let me just put this to negative 5. So first question, is there some way to relate this length to that point? Using all the mathematical knowledge you have gained throughout the years. Is there any way to relate the distance between these 2 points to x, y, and that point?
The distance formula?
Distance formula for 2 points in the plane, right? The distance formula states that the distance between any given points in a plane is equal to the square root of the difference in the x's squared plus the difference in the y's squared, right? That's the formula. Now usually we get 2 points, right? So numerical values we're subtracting. In this case we have an x, y, and a 2, negative 5. My recommendation is put the letter in front on the subtractions. But the distance between points is subtraction. So if I take x minus x and y minus y, we're going to get that. That right there represents an equation that relates to what we're trying to optimize distance. We're trying to make distance the smallest it can possibly be to the point on the line x comma y. All right? And again, that's our initial step. Need to get us to this point. Now the other thing is there's too many variables again. Okay. So right here, this is our equation that relates to variables. So in the last problem, it told us what the volume had to be. I think we did the farmer problem. It told us what the fencing length was, right? Set things in stone. In order to get some variable in terms of the other, they've already started off with an equation relating x and y. Y equals negative 2x plus 8. This expression can go in place of that y right there. So if I do that, that gets me down to d equals the square root of x minus 2, the quantity squared, plus, put here with this and combine like terms, I'm going to get negative 2x plus 13 squared. And just like that, I have a relating equation. Now imagine differentiating this. First off, obviously x minus 2 squared and negative 2x plus 13 squared can be squared, simplified into polynomial structure, right? But then we still have a square root of something, right? Okay. Let me tell you something that's going to help you on a problem with this writing, because this happens pretty often, where you have some radical of some object that you need to differentiate in order to get this. If the square root of a number is there, right, if you have that, square root of a number, or just the number being all this stuff, all right? If the number is smallest, then square root of number is smallest. What that's stating is, if I can make x minus 2 squared plus negative 2x plus 13 squared be the smallest it can be, then the square root of that's still the smallest it can be, right? I can give you anecdotal evidence for that. You ever heard of anecdotal evidence? That just means I can show you where it works. Doesn't prove anything, but I can convince you by anecdotal evidence. Politicians do it all the time. We need to change this law, blah, 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 because this happened. Anecdotal evidence. Just because one thing happened, we have to change the law that has been working for 50 years because it didn't work once. All right. Anyway, but let's just pick two numbers. Let's say 16 and 49. Which one's smaller?
16.
What's the square root of 16?
4.
What's the square root of 49?
7.
What's smaller?
4.
See, whichever one, this number smaller has a smaller square root. Pretty believable, right?
Mm-hmm.
Convince you guys? Twisting your arm a little bit? Okay. So, I don't have to differentiate that thing. I could say, I'm going to go big D because it's not the same as little d. Big D, come on. The marker's not working right. Big D. Okay. I'm going to change it up a little bit just in case they ask me what the distance would be. I want to make sure that I know that this isn't going to answer my question. So if they want to know the actual distance, we have to go right here to figure out the actual distance. But if I want to figure out what the optimal x is, big D will get me the answer. X minus 2, the quantity squared, plus negative 2x plus 13, the quantity squared. All right, and then that's what I want to differentiate, right? I got what I'm trying to minimize, big D, in terms of a single variable x. And I could differentiate that using the chain rule right now. Not that hard. Okay, if I don't want to use the chain rule, I can actually square those things and add them together, right? So let's do that. Most of us like to use the power rule. So x squared minus 4x plus 4 plus 4x squared minus 52x plus 169. Squaring a binomial is what it always has been. Square the first object, double the product of two objects, square the second. The squares are always positive, regardless of the signs of the objects. The double the product is based on the signs of negative 26 doubled, negative 2 doubled, right? And then combine like terms, so big D comes out to 5x squared minus 56x plus 173. So, if I take that problem there and I differentiate it, D prime is going to be 10x minus 56. Set that equal to 0. There are no endpoints on this problem, right? Polynomial functions cannot be undefined, so the derivative equals 0 is the only critical numbers we're going to get. 10x equals 56, so x equals 5.6. All right. Verifying that's our actual minimum, because that's what we're trying to find as a minimum, right? If I test my intervals from negative infinity to 5.6, and then from 5.6 up to infinity, and I pick, let's go 0, and let's go 6, and we're testing this thing here, right? Oh, right, we're testing this thing here. That's close. So that's not going to work. Okay, we're testing this thing here. If I put 0 in, 0 minus 56 is negative. If I put 6 in, 60 minus 56 is positive. Negative to positive is a minimum, so that verifies that what we're looking for is what we found. Okay, it wants the point on the line. Find the point on the line. That means x, y coordinates, right? We figured out the x coordinate. The y coordinate, I substitute x right there, so y is going to equal -2 times 5.6 plus 8. That's -11.2 plus 8, which makes -3.2. Right? So 5.6 comma -3.2 is the optimal point. If we go back to my graph, 5.6 -3.2, which would be about here, that point. Let's just take a look at our optimal line. Maybe it's a little closer. All right. But again, what I picked was kind of close, but calculus found me the exact right answer. What you'll find for an optimal point like that, the closest, is it should be at a right angle. It'd be great if it actually works. Let's see if I can make that a little bigger. There we go. Twist it. No. There we go. There we go. Our optimal point is at a right angle to the other point. So, and if we go back to my guess point, we can see that's obviously not a right angle. So that wasn't the closest point. I don't know how to make that go away. Oh, well, I can't make it go away. All right, so anyway, but that's it. So the point right there. If they ask for the actual distance between the points, if they want to know what is the closest point, or what's the closest point could get, you just put 5.6 back in your distance equation. Okay, that one, not this one. All right. And you would have found the exact distance. The points would be away from each other.